recording. Dang it. Okay. So I just explained all of that without recording it for later. However, it is on the screen. I may need to go back and restate it after we're done. But as a reminder, we've got rational equations here. We set the denominator equal to 0. Just like we talked about here, we set the denominator equal to 0 to find vertical asymptotes. Those are values not in the domain. And then we set x equal to 0, like we did in the third one here, to find the x-intercept. We also did that in the fourth one. We set x equal to 0 to find the x-intercept. And so that will help us in these solutions. We set the numerator equal to 0 to find any x-intercepts. Oh, did I say that wrong? We set x equal to 0 to find y-intercepts. We set y equal to 0 to find x-intercepts. And the reality is it will turn out to be just the numerator we're setting equal to 0 to get those x-intercepts. We find horizontal or oblique asymptotes by comparing the degree of the numerator to the denominator. If they're the same, the ratio of the leading coefficients is the horizontal asymptote. If the numerator is less than the degree of the denominator, the x-axis is the horizontal asymptote. If the degree of the numerator is greater than the degree of the denominator, there's no horizontal. But if it's only greater by 1, then you go ahead and do the division, and the quotient you end up with is the oblique asymptote, which is like an asymptote down here in number 6. It's at an angle. And that will help you find the easiest ways to graph these rational equations. So let's go ahead and try one. I think that would be a good idea. We'll follow those steps. All right, say our function is g of x equals 2x squared plus 1 over x squared. So our vertical asymptotes we find by setting the denominator equal to 0. So there's our vertical asymptote. Also, the domain is everything but that. So negative infinity up to 0, and then 0 to positive infinity. So we've got the domain of this particular rational function, and we have a vertical asymptote. So now we'll find y-intercept by setting x equal to 0. Well, we know that that can't happen because it's outside of the domain, right? So we can say that's a problem. So no y-intercept, because we can't divide by 0. X-intercept we get by setting the numerator equal to 0. We get 2x squared is negative 1, divide by 2, take the square root, and that's imaginary. So no x-intercepts. Because x would equal plus or minus square root of 1/2 I. So no x-intercepts, it's imaginary. Now let's look for horizontal asymptotes. The degree of the numerator is 2. The degree of the denominator is 2. Those are the same, so we look at the ratio of their leading coefficients. Therefore, y equals 2 over 1, which is 2. That's our horizontal asymptote. So now if I turn on our Cartesian coordinate system, I can say, well, at y equals 2, we have a horizontal asymptote I'll just draw that in like that. There is no y-intercept, no x-intercepts, and so our graph, let's kind of pick a value and plug it in and see what we get. What do we get when we plug in 1? Just to get some points to graph with, because we have no intercepts to worry about. We get 2 times 1 squared plus 1 over 2. I'm sorry, that should be 1 squared. So this would be 2 plus 1 is 3, divided by 1 is 3. So at 1, we're up here at 3. Let's try negative 1. Looks like the same thing, because negative 1 squared is the same as positive 1 squared. So again, we're going to end at 3. And I think as we get more points, we will find that our graph comes down and approaches that intercept, and it'll come down this side and approach the asymptote. And so our graph will look something like that. We did our tests. We tested for our vertical asymptote. I should have graphed that out. That was at x equals 0. So that was our y-axis. That's our vertical asymptote right here. We had our horizontal asymptote right there. There's no y-intercept, no x-intercept, and then we just needed to find where the graph occurred in which of those quadrants. So I picked a point to plug it in and see what I would get. And that's what I ended up with. And it seems to work pretty well. Have any questions on that? We'll do another one. Something I do want to mention is that if a factor of the numerator is a factor of the denominator, then that will create a hole in the graph. And I'll show you what one of those looks like here in a minute, because you can cancel that out and just worry about the rest of it. But we also have to account for that when we're graphing. I'm trying to find a really good one here. Maybe I should just, yeah, let's do this one next to kind of highlight this idea of there being a hole. If our function, again, let's use g of x, could be f of x, it doesn't matter, equals x minus 2 over x squared minus x minus 2. Our vertical asymptotes are where the denominator equals 0. Probably factor this. The x times x, 2 is prime, so it has to be 2 and 1. The larger value gets the sign of the middle since it's a negative 2 over here. So x equals negative 1 and x equals 2 would be our vertical asymptotes. Let's go ahead and graph those. So there are some vertical asymptotes. X-intercepts. Well, let's do y-intercepts first. Y-intercept, you set x equal to 0. So we've got 0 minus 2 over 0 squared minus 0 minus 2. Looks like negative 2 over negative 2, which is 1. So we've got a y-intercept of 1. Good. Okay, let's find x-intercepts. And to do that, we just set our numerator equal to 0. So x equals 2 would be our x-intercept. Oh, but see, 2 is a vertical asymptote, so we've got a little bit of a disparity there. So the graph is going to cross at 2, except there isn't a graph there. So we'll see what that looks like here in a minute. Let's take a look at the horizontal asymptotes. So the degree of the numerator is 1. The degree of the denominator is 2. When the numerator is less than the denominator, our horizontal asymptote is the x-axis. So there is a horizontal asymptote. And so it'll approach that without crossing it. So let's see what we've got. Let's pick some values and plug them in. Let's find g of -2. So we've got -2 minus 2 over -2 squared minus -2 minus 2. -2 minus 2 is -4 over 4 plus 2 minus 2. Plus 2 minus 2 are going to cancel. We end up with -4 over 4, which is -1. So at -2, our graph is down here at -1. We could pick some others, but let's try a g of 1. And we get 1 minus 2 over 1 squared minus 1 minus 2. 1 minus 2 is -1. 1 minus 1 is 0, minus 2 is -2. So we would get a half at 1, which is right there. And as we got other numbers, we would find that the graph starts here, comes up, goes through that point, and approaches the horizontal intercept without crossing. And you can see this is coming down. It's going to come down here, go through there. Oh, you know what? Actually comes down here and approaches, but doesn't cross. And we end up with a hole in our graph right there. And so they draw it with a little circle and like that. Because x minus 2 is a factor in the numerator and the denominator, what we could have done, once we factored this denominator out into x plus 1 times x minus 2, if we cross those out and end up with 1 over x plus 1, it's going to look just like the red graph there, except we know that x can't equal 2, and so there would be a hole. And so when you have a factor that's common, go ahead and cancel those out and graph the rest of it. But never forget that what you canceled out will put a hole in your graph. So we went ahead and did the whole thing. Probably should have canceled that out first. I don't think it mattered too much because we still got values that worked. Now, most of the time, you will be given a graph, given a series of 4 graphs, and you pick the one that fits. You will be asked to find vertical asymptotes. Any intercepts, you'll have to type those in, and watch that sometimes they ask you to type in an ordered pair. So watch for that. But they want these particulars that we found in black on the screen, and then they'll give you a few graphs and you pick the one that fits. So graphing it will be pretty easy in MyMathLab because you're just picking the right one. But finding those particulars is just following those steps. All right, there is a homework problem that I want to share with you because it's kind of weird. And it's the last one in the problem. And so I want to share it with you so that you can see what we need to do before you get to it. They give us this graph, and they want us to find the equation for the graph. Kind of weird, huh? All right, let's kind of backtrack and see what we can come up with. I'll go ahead and use f of x. It doesn't matter whether it's f of x or g of x. What matters is what we put over here to the right. So some of the particulars. I've got an x-intercept of -1, which means there's got to be an x plus 1. And where did we get the x-intercept? In the numerator. X-intercepts are in the numerator. So I've got an x plus 1 in the numerator to handle that intercept. Let's see, what else have I got? Just thinking of some of the things we calculated. Here we've got a vertical asymptote at x equals -3. If I added 3 to both sides, I get a factor here. Where did we find vertical asymptotes? In the denominator. So there's an x plus 3 down here in the denominator. And I know that because of the vertical asymptote. Now the other thing I've got here is the hole in the graph, right here. And if there's a hole in the graph, then that means I have a denominator, or I have a factor that is the same in the numerator and the denominator that matches that point at x equals 2. So subtract 2 from both sides, and that gives me the factor that I have to put in both the numerator and the denominator to make that whole. And now the horizontal asymptote is at x equals 1, or y equals 1. We get a horizontal asymptote when the degree of the numerator and the degree of the denominator is the same, which we've already got. We've got x squared top and bottom. And the coefficient, the leading coefficients, the ratio, gives us this value, which is 1, so they have to be the same, so we'll leave it the way it is. So now we've handled x-intercept, we've handled the vertical asymptote, and we took care of the hole. We double check to make sure that fits with the horizontal asymptote, and so we'll go ahead and hit submit. And that will be the right answer. You could multiply those together and have x squared minus x minus 2 on the numerator and x squared plus x minus 6 on the denominator. It should recognize that just fine. But when I left it factored this way, the software was okay with that. And I wanted you to see this because it's not written in the chapter. It's more a question to check to make sure you understand the concepts of finding x-intercepts, vertical asymptotes, horizontal asymptotes, and any holes in the graph. So I wanted to share this with you so that you could see how we go backwards, just to show you that understanding the concept will allow you to create a function from a graph. Again, understanding those concepts. Do you have any questions on that one? This is the last one in the homework, so you'll get to it, but All right, I'm looking for another problem. We're pretty well out of time, actually. So take a look in the chapter. I know this has a lot of stuff. We talked about a whole bunch of things. The most important, I think, not that. Where's our list there? I think this is really the gist of it. This list here, follow the procedure. Set your denominator equal to 0 to find vertical asymptotes. Set x equal to 0 to find the y-intercept, and there may not be one. Set the numerator equal to 0 to find x-intercepts, and again, there may not be any. Then look for horizontal asymptotes. If there is one, there will not be an oblique asymptote. If there's not a horizontal, there may be an oblique if the degree of the numerator is one more than the degree of the denominator. But once you've got all of those things in, just like in our examples, you can plug in a couple of points and see where the graph occurs. It will always approach vertical asymptotes without crossing. It may cross a horizontal or oblique asymptote, but by picking points, you'll usually be able to determine when that happens. And again, in the homework, you'll just be picking graphs rather than graphing them yourself, which will make your job easier for graphing. Because it's pretty easy to eliminate a couple of them quickly once you know these things, the vertical asymptotes, intercepts, and so on. Are there any questions before we call it a day? Okay, what's your question, EJ? All right, back in 4.2. What about graphing polynomials? Okay, do you have a particular homework problem you'd like to see worked out to help find those points? Which problem? Four x cubed minus 6x squared minus 16x plus 24. And they want us to graph that. Okay. Six x squared plus 16x. Why can't I remember? Minus 16x plus 24. All right. So we know that because it's an odd degree and the leading coefficient is positive, that it'll go up to the right and down to the left. We know that. Let's see, could we may be able to do a little factor by grouping. So if I group here and there, I'm going to try it just to see if it works. factor maybe a 2x squared out, gives me 2x minus 3, and factor looks like a negative 8 out. I get 2x minus 3, so it looks like this is working. So I'll factor 2x minus 3 out of those, and I'm left with 2x squared minus 8. So we're setting these equal to 0. So set each of those equal to 0. Add 3 to both sides. Divide by 2. And over here, add 8 to both sides. Divide by 2. Take the square root of both sides. And now we have x-intercepts. Negative 2, plus 2, and 3 halves. Right there. 3 halves is 1.5. So we've got that. Because the graph has to end up this way, the multiplicity on those factors is 1. So the graph is going to go straight through. It's got to turn around and come back. So this is going to come back down, go through the 2, and back. Has to turn around real quick to come up through the 1.5. We could find the y-intercept by setting x equal to 0. And it looks like 24, so super high. It's going to go up off the screen here and turn around and come back down like that. So that would be our graph. And that would be one way to find these points. So that would work. We could also use our rational zeros theorem, which said we needed factors of 24. So that would be a 1, a 2, a 3, 4, 6, 8, 12, and 24, all over factors of 4, 2, and 4. And you can see we've got a whole bunch to pick from. We could do some synthetic division. Looking at our exponents, 3, 2, 1, 0, they're all there. So we could do 4, negative 6, negative 16, and 24. Divide by, say, 2. So you bring down the 4 times 2 is 8, plus negative 6 is 2, times 2 is 4, plus negative 16 is negative 12, times 2 is negative 24, plus 24 is 0. And now we're down to a squared, and we can plug that into the quadratic formula to get the other 2. We know that 2 is one of our zeros. So that's another way we could do it. I think the factor by grouping is the quickest way with this one, but the rational zeros theorem and some synthetic division would give us the same results. Did that help? Sweet. All right. Any other questions? All right. I do want to say that I thought maybe factor by grouping would work. Before I go, I want to say this one last thing. And the reason why is the ratio of 4 to 6 is 2/3. The ratio of 16 to 24, well, it's negative 2/3 really. And the ratio of negative 16 to 24 is also negative 2/3. Because those ratios were identical, factor by grouping should work. So that's one test to see whether that's something you want to consider. And it really only works when I've got 4 terms like we do here. All right, let's go ahead and call it a night. And I'll see you tomorrow. Make sure you get your homework done. We do have our test this weekend, and you don't want to get behind on that. All right, have a good night.